All right, so do y'all remember where we left off with this? I know that I went through the halogenations.
We skipped over the using sulfonal esters to turn alcohols into good behavior.
Did I draw these mechanisms though?
Yeah.
Well, no. You just do the line.
Okay, let's draw the mechanisms. Where did the mechanisms stop?
After
this one?
SOCl2.
Okay. Okay, so really quickly on page 2, before we jump into the stuff that we didn't cover at the review session, I want you guys to make sure that you understand that whenever you're halogenating an alcohol with HX, and remember HX could be HCl, it could be HBr, it could be HI, you're going to typically see this reaction take place as an SN1 mechanism. Why is it important for you to know that this is an SN1 mechanism? Is because you can have carbocation rearrangements. So make sure that you guys recognize that, and the problems that we do at the end of this, you guys will hopefully see how they can exploit your knowledge of this on the exam. So we said that we had gone through the mechanism for this particular reaction, so let's move forward. And I drew out the product for this one, but I didn't talk about the mechanism. So really quickly, I'm going to draw the product. Understand that SOCl2, PCl3, and PBr3 are all SN2 halogenations of alcohols. So what that means is you're going to have an alcohol that is substituted for some halogen, and you're going to get inversion of stereochemistry. So when you take this alcohol off, you're going to replace it with, in this case, a chlorine, and the chlorine is going to be coming out at you because the alcohol was going back. Now from a mechanistic standpoint, what's happening is lone pair of electrons from your oxygen attack your phosphorus and you displace a chlorine. Once that has taken place, that leads you to this intermediate. Now recognize all of these SN2 halogenation reactions are done in pyridine, which is a good base. So pyridine will come along and remove a proton from the oxygen. These electrons will swing back, neutralizing the oxygen. What we've done in effect at this point is we've turned our phosphorus into an excellent leaving group, or excuse me, our oxygen into an excellent leaving group. So the chlorine that we displaced initially can come back and it'll attack SN2 backside, kicking your leaving group out. And that's how we end up with this final product. So again, I want to stress that this particular reaction is an SN2 reaction, as is the SOCl2 on page 3 and the PBr3 mechanism on the bottom of this page. So similarly, PBr3 and pyridine will add a bromine, SN2, in place of the oxygen. Same type of mechanism that we did above, except we are swapping out chlorines for bromine. Lone pair of electrons will reach out, attack the phosphorus, will kick off our bromine, leading us to this intermediate. Pyridine, again, is a base. It will deprotonate our oxygen, leading us to this structure. Our Br- can come in and attack from the back side, kicking our leaving group out, and we get our final structure. All right, so those are the halogenations. Again, it's important, and I'm going to write this down just to emphasize, because I know that y'all's test is tomorrow, and y'all are going to be freaking out. HX reactions of alcohols have an SN1 mechanism and can undergo carbocation rearrangement. SOCl2, PBr3, and PCl3, reactions of alcohols, are SN2 mechanisms, or have SN2 mechanisms. which essentially means we will get inversion of stereochemistry and there are no carbocation rearrangements. Yes?
Would you be able to do like a quick problem that has carbocation rearrangement?
We'll do those at the end.
Is there a preference for SaCl2, PBr3, or PCl3? Okay.
It just depends on whatever. So y'all know from the previous exam, he might give you a reactant and a product. So if you're doing a substitution of an alcohol and the reactant and the product has a bromine, you want to use PBr3.
Yeah.
That's about it.
Okay.
But other than that, no. All right, the next thing that we want to look at is how can we turn alcohols into good leaving groups aside from using something like SOCl2 or PBr3 to substitute it for a halogen. And the way that we'll do this is we will use sulfonyl esters. The major sulfonyl ester is the tosylate. The long name is toluene sulfonyl chloride. And what happens is we will remove the hydrogen from our OH and replace it with this whole group minus the chlorine. What that does is it simply causes the oxygen of our alcohol to become a very good leaving group and allows us to essentially substitute the oxygen of our alcohol for some nucleophile. So essentially what's going to happen here is we'll react tosyl chloride with pyridine and our alcohol. We will remove the hydrogen and replace it with a tosyl group. Note that the stereochemistry here does not change, it's still dashed. Now if we react this structure, which is essentially an alkyl halide because it's a good leaving group, with some nucleophile, we have a secondary alkyl leaving group, we have a good nucleophile weak base. What mechanism is this? SN2, so we will end up inverting the stereochemistry. So this is SN2 and it's a single inversion. Now just so you guys know, these other structures are examples of sulfonyl esters as well, but the most common one that you'll see on your exam is the tosylate. Now let's compare what's happened here to us halogenating the alcohol first and then doing our SN2 reaction. So we know that when we have a alcohol and we react it with PBr3, POCl3, or PCl3, or SOCl2, we will remove the alcohol, replacing it with a halogen, and we'll have inversion of stereochemistry. So this is an SN2 reaction. Now we have a secondary alkyl halide reacting with a weak base good nucleophile and a polar aprotic solvent. So what is this mechanism? SN2. So what has happened here is we have two inversions, and two inversions equal retention. So double inversion equals retention. So in this last SN2 reaction, we'll add N3, but note what has happened. Our N3 has the same stereochemistry as our original. So again, we'll go through a series of problems regarding how they can exploit your knowledge of this on your exam, but it's important to know that tosylate allows you to undergo single inversion. If you halogenate the alcohol first, you'll get an inversion, and then when you do another SN2 reaction, you'll get another inversion. So halogenation of alcohols will allow for double inversion, whereas tosylate allows for single inversion. Questions on that? Do y'all see the differences between these? If I had asked you to start from this structure and I wanted this one, you would have to go through double inversion. If I asked you to start from this structure and go to this one, you would have to use a tosylate and go through single inversion.
So would you write that as like a 1 and then the tosylate chloride pyrimidine and then 2 and 8?
Exactly.
Okay.
Exactly. All right, so the next thing that we'll look at is the dehydration of the alcohol. Now, dehydration of alcohol will take place in strong acid. Understand in general, whenever you're dehydrating an acid or alcohol in strong acid, this is an E1 mechanism. What is the significance of that? Well, understand that E1 mechanisms have the ability to undergo carbocation rearrangements. So watch out for carbocation rearrangements anytime you have acid-catalyzed dehydration. Generally, you will form the more highly substituted double bond in these E1 reactions. So the mechanism works like this. You have a strong acid which donates a proton to your alcohol, and in effect turns your alcohol into water, which is a decent leaving group. Water will leave, and remember, the hallmark of the E1 reaction is the formation of the carbocation, so when water leaves, we form the carbocation. Notice we have two adjacent hydrogens that we could pull off, but we're going to specifically pull off the one that will lead us to the more highly substituted double bond. So we pull this one off instead of this one. So water will come back as your base, remove this proton, these electrons will fold in, and that's how we get to the final structure. Questions on this? Now, if we want to avoid having to go through a potential carbocation rearrangement, but we still want to dehydrate an alcohol, we can get around the carbocation rearrangement problem by using POCl3 and pyridine. POCl3 and pyridine is always an E2 reaction. And again, it allows us to circumvent forming a carbocation. So let's look at the mechanism for this. So the product is going to be the same, but note that this is E2, and so we don't have to worry about carbocation rearrangements. So what's happening here? Electrons attack phosphorus, we kick out a chlorine. Chlorine comes back, deprotonates the oxygen. That leaves us here. And then pyridine, which is a decent base, comes in, removes a proton. These electrons fold in, and then we kick the leaving group out. So again, that's kind of a mouthful, but understand that what they're going to be trying to do to you on this test is they're going to, again, try to trick you into using acid-catalyzed dehydration as opposed to POCl3 or vice versa. And they'll do that by giving you problems where a potential carbocation could rearrange, but you don't want it to, or you want the cation rearrangement, but you end up choosing the wrong reagent. And probably didn't make very much sense what I just said to you guys, but let's do some problems. We've already gone through all these oxidations at the review. Don't worry about this mechanism. Allegedly, your professor just wants you guys to know the oxidations, but doesn't really care about you guys knowing the mechanisms for the oxidations. And this is the only mechanism in the book anyway. All right, so if we react this alcohol with SOCl2, what's going to happen in pyridine? Where's the chlorine going to go? Okay. And just for emphasis, let's make this wedged. So where will the chlorine go? Where the OH is. And it will be dashed. Now what about HBr? If we use this same structure and we do HBr, what happens? What kind of rearrangement? You're right. Methyl shift. Because remember, HBr, HCl, HI are SN1 mechanisms when you're halogenating alcohols. SOCl2, PBr3, and PCl3 are SN2 mechanisms when you're halogenating alcohols. So this is what I mean by them kind of teasing out your knowledge of the mechanisms for these reactions. Other questions?
Could you possibly draw arrows for how you got
to this? Yeah. I'll do the shorthand version. So I think everybody knows that We'll protonate the alcohol, turning it into water. Water will leave, and you'll end up with this, right? You'll end up with a methyl shift. And now your cation is here. Br minus then comes back and attacks the cation, and that's what takes us to this problem. What was that?
Oh, I hate her. So you do that because it's an SN1?
Exactly.
Okay.
All right, so moving forward, H2SO4 in heat does what to this?
Makes a double bond.
A dehydration.
Dehydration. Tell me about this dehydration.
That's double bond. That's E1.
It's E1, which means what should the product look like?
Be double bond in between like the methyl and the OH. Like
There's
and then
going
they'll
to be a
substitute
methyl
it,
shift.
substitute a double bond.
So that's a methyl shift too.
This is a methyl shift as well. What about this NPOCl3 impurity?
It would without a methyl shift since it's like
So it's E2. And the only place we can remove a hydrogen if this is not going to have a methyl shift is over here. So we end up with this double bond. Now this is a little bit of a different set of reactions, but you guys need to know these. What happens when we react a primary alcohol with chromic acid?
it has carboxylic acid.
Correct. It's oxidized to the carboxylic acid. Primary alcohol with sodium hypochlorite and acetic acid. What does this do?
Aldehyde.
Correct. It stops the oxidation process at the aldehyde. Now in this instance, secondary alkyl halide, strong sterically hindered base, what happens?
E2.
E2. Be more specific though. Strong sterically hindered base. What was that?
Oh, backside attack. So.
Well, antiperiplanar, but there's something else. When I say sterically hindered base, you know how normally we're supposed to get the more highly substituted double bond if we can. Sterically hindered base, no matter what, you go for the least substituted. So this is what this will look like. What other case will give us the least substituted double bond in an elimination reaction? Fluorine is the leaving group. Now when we react this with KOH and ethanol, we now aren't going to necessarily get the least hindered, right? But we need to get, we're not necessarily going to get the least hindered here because we can rotate around. So in order to figure out the stereochemistry for this E2 reaction, we have to turn our chlorine antiperiplanar to our leaving group. Now for those of y'all that were here when I went over this SN1, SN2, E1, E2 stuff right before Thanksgiving, I did give you guys an example of this, and Morrison's done this once or twice. In most of the examples I've given you, either at the review or in your supplement or mock exam, I've given you a situation where the two things that are in the plane are pointed opposite. But note what happens here. The two things that are in the plane are pointed in the same direction. So how do we rotate this so it's antiperiplanar? You half rotate. So let's half rotate the side with the chlorine. So we want to rotate the chlorine such that it's into the plane. And so when we half rotate the chlorine into the plane, it's already back. We're going to bring it up front. And so what's going to happen is the hydrogen, I'm going to go ahead and draw it in. The hydrogen will be out front still, but it will be pointed down. The methyl group will be pointed down, but it will be in the back. So that's a half rotation. Now, when we rotate the hydrogen that's in the back into the plane and pointed down, what happens to the methyl group?
Dash.
Dash, good. Which means the ethyl group is wedged. So what is the stereochemistry of this product after the E2 reaction has taken place? E. Okay.
And for this one, it doesn't matter which side you put the ethyl on, right?
No, because they're both methyls, but if they weren't both methyls, it would make a difference. Yeah. Other questions?
Can you do that with the Newman projection too?
Yes.
Thank you.
Mm-hmm. Wait, are you asking me to do it, or are you saying can you do it?
Both.
Yes, you can do it, and y'all need to watch out for those Newman projection. I didn't take that workshop down yet. I'm not going to go there right now just because when I did it initially, it took me a minute. I don't know if y'all watched that video. I'm like, wait, something's wrong. And then somebody in the audience was like, yeah, that doesn't look right. So watch that video and just be aware that there might be an issue with the Newman projection. And if y'all have more specific questions, just come into the office. We'll do it on the board. All right. Now, obviously, this can look a little scary, but this is a real potential problem that you could see on your exam. We're starting off with this alcohol. We're going to some substituted structure where we've popped the alcohol off, and we ended up with a substituted structure that was inverted, single inverted. Yeah, singly inverted, yes. Sorry, my mind is struggling right now. So, single inversion, what do? Tosyl chloride and what? What's the next step? And some polar aprotic solvent. So I'm sure a lot of you guys looked at this and you were like, oh, there's so many boxes, I don't know. But if you can talk, like you did, you talked yourself through, you saw what the difference between this and the final product was, and you were aware that you needed a single inversion of an alcohol, and that's how you filled in all these blanks, okay? Now, if we're going from this structure all the way down here, what do we notice? Double inversion. So what should we do first? Tosylate single.
One of the P's.
I think I have too many boxes here.
Well, what if
What were you saying?
I was just going to say if we just redraw the alcohol color there instead of across the other boxes. Like, it could just be the same thing instead of being another.
Oh, yeah, that would be fine. You're right. You could do that. And that's probably what I intend. Maybe I just, because there was no box here, maybe I just forgot to erase it. I don't know. All right, so what should we put next to this long arrow that we've just added? NaNH2. So you guys aren't that bad off. I was a little bit worried about y'all, but y'all seem like y'all might have it together a little bit. So NaNH2, we'll use DMF, which is polar aprotic, and we get our second inversion. Now we're done. Now what does MCPBA do to a double bond? Oxidation. Remember, the stereochemistry of the double bond dictates where the substituents of the epoxide will be. They are trans, so they must stay trans in the epoxide. You could just as well draw this wedge. That's fine. What does Br2 and H2O do to this double bond?
It's a Br on each side of the double bond.
Careful, H2O.
Oh, a Br on one side and an alcohol on the other.
Different.
Good.
Anti.
Anti. And what would happen if one side was more substituted than the other? Where would the OH and where would the Br go? Good. You guys are making me smile a little bit here. All right. Now, second way to make an epoxide is to do dehydrohalogenation of the halohydrin using a strong base. So NaH, I think Jackson used tert butoxide in class. NaH or tert butoxide will work, but you will essentially snatch the proton off of the oxygen. The negatively charged oxygen swings down and you kick the bromine out. That leads you to the epoxide. Lastly, PCC does what to this compound? What is PC? Makes a ketone. Okay, 25 minutes and 48 seconds. Questions?
Could you also write tert butoxide as T-BuTO minus?
Yep, that's shorthand.
Why did you do the half rotation for the last one and last one?
Because, so her question is, why do we do a half rotation here? Because right now, the two things that are in the plane are syn-periplanar. You need them to be anti-periplanar. So you need to rotate one of these halfway in order to get anti-periplanar.
So when you rotate half,
It looks like you rotated the other half too.
Well, I rotated the, because the plane though is still down though. So the thing, we ended up having to rotate the hydrogen into the plane, but the thing that's in the plane on this side is still pointed down. But we did the half rotation on this side such that the thing that's in the plane is pointed up. So no one understood what I was saying? Okay, yeah. I'm like, okay, all right, just make me.
I just don't understand how you know what stays, like what goes wedged and what goes dashed when you do the half rotation.
When you do the half rotation, depending on, so half rotation, you're rotating the chlorine such that it's in the plane. So that means that the hydrogen is still going to be wedged, but it's going to be down.
But how do you know that?
Why wouldn't it
Why
be
does it do
dash?
that?
So think about it from this perspective. The thing that's in the plane right now is this, right? The thing that's going back is this. The hydrogen is coming out at you. If you want to rotate the thing that's going back into the plane but up, half rotation. Y'all see that? I'll do it again. This is in the plane, down. This is back. This is coming out at you. We want, in this case, like in this problem, the thing that's going back, we want it in the plane and up. Half rotate. Now it's in the plane and going up, but the thing that was coming out at us and was going up is now coming out at us and going down. Okay? So you have to kind of think of it in three space.
This might be a good test to break out the
Maybe.
Could you show that with like a full rotation with those to kind of understand like what gets changed to?
Yes, does everybody want to see that? I was just asking because that way I can start the upload. Let me just start the upload.